question is, where do earthquakes originate? We are in a convergent margin in a subduction zone, where one plate goes underneath the other one. So a lot of sediments and rocks are being squeezed during this process, actually. And the fluids are interacting with the solids. These fluids interact and equilibrate with the rocks and sediments that they are seeing. So they change the chemistry. Based on the chemistry, we can tell you from which temperature it comes and from what depth it comes, if we know the geology of the area. So that is one of the things that we can tell. And that's very interesting. For example, if we get an earthquake here, the question is, where do earthquakes originate? And if we can capture the fluid which is associated with such an event, we can say, okay, this earthquake came from this region. The process of the earthquake, where does it initiate actually? And the fluids can tell us. They are messengers from depth. So if we really want to know exactly what is happening there, we have to look at the fluids, and the fluids tell us what the fluid rock interactions were, at what temperature and pressure, and from where they came. So that is one of the main objectives they were trying to see here. And they tell us also what rocks are there and what are the reactions. Because you know, when you take a rock and seawater at different temperature and pressure, the reactions are different. Because at each temperature, different minerals dissolve more or less at higher temperature and higher pressure. If you take a fresh basalt and you melt it in the laboratory, you need about 1100–1200 degrees centigrade. If you add some fluid to it, you can lower the temperature to 800–900 temperature. It's a flux. Fluids are flux. So the fluids are helping to melt the rocks at a lower temperatures, pressures than otherwise when they would be dry. So that's another process which the fluids are helping. Chemistry changes continuously. And because of this advective force in subduction zones, we can see things coming from great distances and great depth. Places where you subducted different rates, places where different sediments which are involved, okay, different angles of subductions. So you take these tectonic, geologic, variables, and you're taking end members, and eventually you're trying to extrapolate. It will not be very precise, but it will be within the ballpark to see if it does impact ocean chemistry or not, correct? And ocean chemistry determines, life in the ocean determines the atmosphere. It determines, that's one of the most important things to see the history of ocean chemistry, because ocean chemistry tells us about how Earth functions, the interaction between the land and the interior of the Earth and the atmosphere. And the ocean, if you know how to read the history of ocean chemistry, you can reconstruct the history of interaction of land, interior of the Earth, and the atmosphere. Because seawater chemistry does tell us how Earth functions between exterior processes and interior processes, that's why it's so important. So we like to have very high resolution seawater chemistry. And there's a nice example when hydrothermal fluids were found in the ocean. It revolutionized the whole understanding of how Earth worked, because they impact seawater so much. We didn't know anything about it, so we used what was available actually to interpret the interaction between exterior and interior processes. Suddenly there was a solution, an input which was not known, it was a frontier, and changed the whole understanding of these processes. And that's where we are with subduction zones. If you look at the input into the ocean, what are the major inputs? River, Rivers are a major input, and hydrothermal systems. These are the two major inputs. Hydrothermal system gives us information about the interior of the Earth, and the rivers about superficial processes. Now, subduction zones are related to both, actually, and that's a frontier which is still open-ended.
Okay, let's talk about some instruments. Where do you want to start? Anywhere. You want to start like how we process this stuff or what? Have you gone through this with Miriam and Marta? Okay. So unfortunately, we're not processing samples, but the way that it works, you saw the squeezers earlier. What we're looking at is the pore waters, or the fluids that are contained within the sediment matrix on this cruise, and they tell us a bunch of things about the history of the fluid as well as the history of this particular subduction zone. So what I'm most interested in is using the fluids as tracers for carbon cycling, organic carbon cycling in marine sediments, and how that interacts with the ocean. I'm interested in looking at in situ fluid rock reactions that are happening in the pore space, which alter the fluid chemistry, which then ultimately affects what the chemistry is of the rocks, as well as what what happens with seawater chemistry over time. And I'm also interested in using the fluids. They flow through more permeable horizons, especially in these kinds of active margins. One of the first things we do is we analyze the water, the pore water sample for alkalinity. They flow through these horizons and provide information of, one, what the hydrogeology is, what the fluid flow pathways are, and how the four arc of subduction zones de-water. So you can use that to trace flow horizons, which is very important for looking at answering questions about pore pressure evolution with depth, but as well as how these fluids impact seawater chemistry over time. So as soon as the sample's off of the press, we run it through this instrument, which is an ion chromatograph. And the way that it works is, let's open it up. You can show this. So we use the chemistry of those fluids as remote sensing tools in a sense, since the fluids have migrated from a different source region than what's going on in situ, it carries a distinct fluid composition. And that fluid composition we use to tell a bunch of different things about the history of that fluid. We can use it with the chemistry that we're measuring out here in shore-based to understand the temperature of that fluid, some of the fluid rock reactions that has produced that chemistry, and how it relates to the basically overall architecture of the subduction zone. And so we use it as a tool to understand where fluids are coming from and how they migrate through the subduction zone. And without the chemistry, you really can't do that. Then bromide comes out, which is another anionic species. It's a halogen. And then sulfate comes out afterwards. And so each one has a different retention time in this column. How does it help you with the future? So that's that. This is not my domain, but it's another analysis that's done pretty quickly. So these two are gas chromatographs. Okay, because these fluids are coming from a source region that is beyond the depth of drilling currently, it provides information on phase transitions and the temperature of those phase transitions, which are and as well as pore fluid pressure, which are all very important, actually key ingredients for what causes seismogenic behavior in subduction zones. And chloride basically, in my opinion, is the most important element we analyze for because it's conservative at the temperatures that we're looking at. So if you go from a mineral that has stable sliding characteristics to one that has stick-slip characteristics, the fluid chemistry that we are getting can be used in a way we invert it to try to understand what those mineral transitions may be. So we can tell whether or not water's been added to the pore water from mineral reactions, or if water is being consumed. And I guess, what I can say, is that from many decades of looking at these fluids, what we see is that they come from a dehydration source. Okay, so we see evidence that clay minerals are dehydrating, and they're dominated by smectite to illite transition. Okay, the fluids that are coming from the deeper source. And that always been a hypothesis of being one of the main drivers for why you have stick-slip behavior on the subduction thrust is that during this phase transition, you release a lot of water, and that water lubricates the fault zone. And once that phase transition is complete, which is around 100 to 150 degrees C, you don't have the overpressure, you don't have the over-pore pressures, and you can go back to more of a stick-slip behavior because you're not lubricating the fault zone. So chemistry has been very helpful in identifying a lot of these basically phase transitions or reactions that occur in the subduction zone that may be controlling seismic behavior. Let's see, what else do we do? So we have this, that, ion chromatograph, gas chromatographs. What have we learned on this expedition? Yeah. Last thing is what Eric is working on. Eric, do you mind if we shoot you for a second? You know, I mean, we've learned a lot of, I think, through this expedition on how subduction zones evolve through time, basically, and information that we didn't have before. So without coring here, we wouldn't have gained some of the insight that we'll have after this cruise on the evolution of subduction zones, the impact of seamounts, subducting in subduction zones, and the change from periods where you were accreting sediment to periods where you may be eroding material from the subduction zone. So I think from a general sense, that was something that was unclear before this expedition, and we've gained some new insight into some of these processes in this expedition. Yeah, and with respect to this, I mean, there's interesting things to say, but we're still working on it. Yeah, yeah.
It is hard for me to convey the absolute thrill that is involved in doing science. It is, to me, a privilege to be able to do this kind of work. It is something that is innate to human nature, to ask questions, to ponder, to wonder, and to have the opportunity to pursue this is and there are two aspects of it. You know, you can make a prediction and you could be right, and that is very exciting. However, as a scientist that I respect a lot taught me a long time ago, he says, the time I learn the most is when I'm wrong. Because I predicted the system will work this way. If I find that it works this way, then it sort of confirms something that we already know. But if we find something that is not what we predicted, then we really need to understand, how is this working? What we need to find out here in order to understand what generates earthquakes is how the entire system works, where two plates meet. What kind of processes are involved in the subduction, the type of subduction, the mechanisms, what happens when there are seamounts that are coming on the plate, what happens when they meet the other plate. And we cannot sample everything, and we cannot sample at depths. So we take small snapshots at the system that allow us to infer, to predict what's happening in the overall context. You can imagine if you're looking at an outcrop, you know, you're going to do field geology, you know, and you could see how the faults form. You could see the entire context of it. Here we have a thin, you know, 6 centimeter view of what's happening at depths. So we're using a variety of tools to try to understand, and fluids, because they move along faults. And they are very distinct. We can very, very clearly tell certain processes by the composition of those fluids. We're able to contribute to the overall understanding of the system. And it is not, my science is not in itself I cannot answer the questions with just what I do. This is a team effort. This is a group of interdisciplinary people with various expertise where we're putting together all this information based on a very small sample of the formation to try to understand a process as big as what generates earthquakes. I would hesitate to say that the work we're going to do here will answer all the questions related to earthquake seismicity. No. And science moves in very little steps. We all contribute a little bit. And perhaps at the beginning it is only interesting to a small group of people. So it's a building, it's an accumulation of knowledge that lets us to understand the big picture. I think one of the most fascinating things about the work that we do is that we can ask questions and we can pursue answers to the way the planet works. Being able to pose questions and pursue that idea to try to understand an observation, to me that doesn't get any better than that. It's fantastic.